All right, finishing out the rest of this worksheet, we're going to start with, what's this supposed to be equal to? Number 11, number 11 is supposed to equal sine theta. It's important to have a goal in the end. So, all right, we're going to work on this side first. And I would say that I don't see any obvious identities. So I'm going to change everything to sines and cosines. So quotient identity says tangent is sine theta over cosine theta. And 1 plus secant will be 1 plus 1 over cosine theta. All right. Now, we used this shortcut pretty often with rational expressions. How do you simplify a complex fraction if it's got different denominators in it? So remember, there were two ways. You can either get a common denominator on the top and get this fraction, same on the bottom, and then change this to a multiplication problem, or the shortcut that I always use, because it's a lot less writing, is to multiply by 1, but you're multiplying by 1 in terms of whatever denominators you see. So I see cosine denominators, so I want to clear those out by multiplying by cosine on the top and cosine on the bottom. And you're allowed to do that because you're just multiplying by 1. It's just sort of a special case of 1 that's going to help us. All right, so the first thing would become sine theta times cosine theta. The second term, the cosines would cancel, so you would just get plus sine theta. In the denominator, 1 times cosine is cosine. 1 over cosine times cosine is 1. And then I'm kind of out of room, so I'm going to go sideways here. Then take a look at what you have in the top. You can factor out a sine theta, and that would leave you with cosine theta plus 1. And you still have cosine theta plus 1 in the denominator. And so those expressions divide out to 1. They're allowed to cancel. So we get sine theta, which is what we were trying to prove in the end. All right, next one. I'm going to start on the left side. And again, you can change to sines and cosines, or I do see a Pythagorean identity here, so I'm going to change that. So 1 minus, maybe we should make tangent squared sine squared theta over cosine squared theta. And then 1 plus tangent squared is secant squared theta. Or if you wanted to, right away, you could have also changed that to 1 over sine squared theta. So I'm going to kind of do what I did in the last problem. So, all right, so I've got 1 minus sine squared over cosine squared. Change secant squared to 1 over cosine squared. You could say that's the same as times cosine squared over 1, or you could do the same trick I did before and say, I want to clear out this complex fraction, so I'm going to do this. So there are a lot of ways to show the steps, and they're all kind of equivalent. So maybe you do this in a few less steps than me. It just kind of depends on what you're going to show. So if I go this route, I'm going to get cosine squared theta minus sine squared theta. In the bottom, cosine squared times 1 over cosine squared is 1. Now look to the right side. You're trying to get 2 cosine squared, so there's no sine squared anywhere. That means that you should sub out your your sine squared with a 1 minus cosine squared. That's the rearranged Pythagorean identity that we've used quite a bit. And if you do that and distribute the negative, you're going to get cosine squared plus cosine squared, so 2 cosine squared theta, and then the 1 becomes a minus 1, and that's what we were trying to prove. Okay, for this next one, I don't think it matters which side you start on for this one. So let's say I start on the right side. Usually if I see things that are not sines and cosines, I consider that the more complicated side. So let's change these to be 1 over sine theta. It's the reciprocal identity. Quotient identity for cotangent is cosine theta over sine theta. So these already have a common denominator. So we can make that 1 plus cosine theta all over sine theta. And actually, we're done. That's what we were trying to show. So that was actually a pretty short one. Okay, next one. Let's start on the left side. Secant is 1 over cosine theta times sine theta. Tangent plus cotangent, so sine theta over cosine theta plus cosine theta over sine theta. All right, I'm going to use my clear out the complex fraction trick. So there's a denominator here of cosine theta. There's a denominator here of cosine theta. Here's sine theta. So we're going to have to multiply by both cosine theta and sine theta to clear out both fractions. Okay, so when you do that, so this is just sine over cosine, right? So the cosines are going to cancel, and you're going to get sine squared theta. That's a good sign because we're trying to get that in the end. In the denominator, when you multiply cosine sine times sine over cosine, the cosines will cancel. You'll get sine squared theta again. When you multiply that by the second term, the sines will cancel. You get plus cosine squared theta. And we should recognize that Pythagorean identity, sine squared theta over 1, which is sine squared theta. All right. On to number 15. So I see a couple of binomials that are being squared, so we should probably just square them out. So sine plus cosine will become sine squared theta plus 2 cosine theta sine theta. In any order, I could have written sine cosine. Plus cosine squared theta, and then plus, when we square out the second binomial, we get another sine squared theta minus 2 cosine theta sine theta plus cosine squared theta. So there's a plus 2 cosine sine and a minus 2 cosine sine that cancel out. Sine squared plus cosine squared is 1. There's another plus sine squared plus cosine squared. So 1 plus 1 is 2, which is what we were trying to show. Starting on the right side here, I'm just going to divvy this up so it doesn't get confused. Remember, what you're not allowed to do is divide like this. That's an upside down heart, and we can't do that. That's illegal mathematically. If it were flipped, we could split it up, but it's not. So instead, I'm going to work on this a little bit. Now, this may or may not jump out at you, but secant squared minus 1 is a rearranged Pythagorean identity. So I'm going to swap that out. I'm going to make this secant squared theta over tangent squared theta. And then I'm going to rewrite things in terms of sine and cosine. I'm trying to get it to be 1 over sine squared to make it cosecant squared. So 1 over cosine squared theta over sine squared theta over cosine squared theta. Now, when I show my work for this, I usually don't do a fraction over a fraction. Instead, if it's just divided by something like tangent squared, instead of saying divided by sine over cosine, I multiply by cosine squared over sine squared. So you can think of that two ways. You can write the divided by a fraction and then multiply by the reciprocal, or you could say like divided by tangent squared is the same as times cotangent squared, and then you could write it like this. But either way, those cosine squareds cancel, and 1 over sine squared theta is cosecant squared theta. All right, so let's look at this next one. So what's more complicated, tangent squared times sine squared or tangent squared minus sine squared? It's interesting that those are equal. Usually addition or subtraction has more to do because you can do common denominators and things. So let's start on the right side. Let's make this sine squared theta over cosine squared theta minus sine squared theta. You can make it over 1 if you want to. So the common denominator I need to set up is cosine squared theta. The first fraction already has it, so I just write down sine squared. The second fraction would have to get multiplied by cosine squared over cosine squared. So that becomes minus sine squared theta cosine squared theta. So they're both over cosine squared. And we used this a little bit earlier, a couple problems ago. Notice that you can factor out a sine squared from the numerator. Sine squared theta times 1 minus cosine squared theta. over cosine squared theta. And always keep an eye on what you're trying to prove. You don't want to just keep blindly doing stuff. So look over here. Tangent squared we have, sine squared over cosine squared. And we do have sine squared as well because 1 minus cosine squared is sine squared. So sine squared over cosine squared is tangent squared theta, and 1 minus cosine squared is sine squared theta. All right. Number 18. Now you could start foiling right off the bat, or you could change to sines and cosines first. I can't remember how I did it in the key that I posted, but I'm just going to foil this to begin with, I think. Also, side note, sine plus cosine is not 1. It has to be squared. Remember, you can't just square root. If sine squared plus cosine squared equals 1, it's not true that the square root of each term is equal. So if I FOIL, I get sine theta tangent theta plus sine theta cotangent theta plus cosine theta tangent theta plus cosine theta cotangent theta. And then let's look at sines and cosines. So this would be tangent sine over cosine. So this is going to be sine squared theta over cosine theta. So I just did sine times sine to begin with. Sine theta times cosine over sine. So that's just going to be plus cosine theta. Cosine times sine over cosine is going to be plus sine theta. Cosine times cosine over sine is going to be plus cosine squared theta over sine. All right, so if we try setting up maybe a common denominator or something, looks like they would all need to be over sine cosine, although that's going to get kind of messy, isn't it? So let's see, we're trying to get it to be 1 over cosine plus 1 over sine theta. Yeah, let's do a common denominator. So the common denominator would be cosine theta times sine theta. I'm hesitating because I'm thinking, wow, this is getting kind of long, so I might have to reevaluate how I started. Maybe I picked a long way to do this, or maybe I made a mistake somewhere. I don't know. Let's just see what happens if we get a common denominator, and I'll decide if I have to go back to the drawing board or not. All right, so sine cubed plus, this would need both, so cosine squared theta times sine theta. Yeah, I think this is going to get kind of ugly, right? Plus sine squared theta cosine theta plus cosine cubed theta. Eeks, okay. And there's probably a little bit of factor by grouping that could happen in there, I guess. Let's see. Yeah, let's see how that goes. Okay, so I'm sure that I did this a different way on my key. Let's factor the top by grouping. We can take out a sine theta. So that's not bad because that gives you a sine squared theta plus cosine squared theta. Okay, that's 1. That's a good sign. And then I can factor out a cosine theta. That gives me another sine squared theta plus cosine squared theta. All right. So it was ugly for a second, but I got somewhere with this. This is 1, and this is 1. So now it's sine theta plus cosine theta over cosine theta sine theta. Okay, remember we're trying to get here. You have a binomial divided by a monomial. Even though there's two things down there, they're being multiplied. So you can use, we informally call this the heart method because you're allowed to divide each term by that denominator. Kind of looks like a heart. So that would leave me with sine over cosine sine would leave me with 1 over cosine. And in the second term, the cosines cancel out. And that's where we end up, secant theta plus cosecant theta. Let's take a look at number 18. How did I do it on the key that I posted? Okay. On the key that I posted, no, take a look at this. Here's another way to do this one. you can add tangent and cotangent together first, and that makes things a lot nicer. So notice how I still ended up here in the end. So this is an example of there are different ways to tackle these. I made this pretty difficult. But how did I know to factor by grouping? Well, I saw 4 terms, and that's sort of the only thing I could go do from there. So something to try as you're doing those. Okay, we have just a few more. Actually, I think I'm going to have to stop for this page because I'm out of time, but I will pick this up and post another video for the last 6 that we have.